So our expert panel consists of members of the department and the producer, one of the producers of the show that you just witnessed. So each of the, I've seated people appropriately underneath their names. We have Dr. Arpita Roy, Dr. Jason Wang, who both work on exoplanets, that is planets orbiting around other stars. Dr. Ilaria Caiazzo and I are the non-exoplanet people. She works on compact objects, which is to say neutron stars, black holes, white dwarfs, and I work on galaxy evolution and formation over the duration of the universe. And then our producer, André Bormanis, has been a producer as well as a writer, not just for this show, but the previous season of this, as well as many other shows that you're probably familiar with, like Star Trek The Next Generation, Deep Space Nine, Voyager, and a variety of other shows. So we're happy to take questions about the topics that were covered both in this wonderful program as well as just in general about space science and astronomy and astrophysics if you have questions. And you always have a question.
Something that was mentioned in the program, I'm just wondering, why is a body in orbit around another body more likely to be tidally locked if its proximity is closer? Why does proximity make something more likely to be tidally locked?
So it's basically it's the fact that when you're much closer, the objects are no longer single point sources. You actually see them as their 3D selves, and because of that, as it's orbiting, you're not just like, it's not like when the Earth's orbiting the sun. It's kind of like the sun is pulling on a point source, like a dot that is the Earth, because it's so far away. Whereas you're much closer, you're not pulling on a point source, you're pulling on a disk. And every time you pull on the disk, you can basically turn the disk back towards us.
So the kind of simple way I like to think about it is that the planet itself is rotating and it's revolving around the star. And so the lowest energy state, the most stable state it can be in is to rotate and revolve at the same period. And so the same face always turns to the star. Because the gravitational pull is just stronger when it's closer, and so balancing those out matters more when it's closer than when it's further away.
I'd like to know, are all planets revolving out in space? Do they revolve constantly?
So we haven't measured too many planets' revolution periods, but physically we think that they would all revolve. This just comes from one of the laws of nature, the conservation of angular momentum. So anything that's rotating will always be you can't destroy rotation. So once you have anything starting to rotate, they will keep rotating. So we think there's nothing. It's really hard to keep something static.
Yeah, they usually start spinning as they form out of the disk, but there are things like rogue planets that we see that are probably flying around without being attached to a star, and we actually don't know if those rotate, I suppose.
So, Mr. Bormanis, in thinking about the target audience for Cosmos, how do you think Cosmos and shows related to Cosmos how has it impacted the younger generation's affinity for STEM? And was that part of the intent to make STEM more accessible, or maybe to make an electorate more supportive of funding such efforts?
Sure. Oh, thank you.
Yeah, I think that the goal has always been to inspire, especially younger people, but not exclusively younger people. And Carl Sagan had an amazing gift for storytelling and for writing. He was obviously a very brilliant astronomer and physicist, but unlike many people in that field, he had a gift for writing and communicating, and he wanted to share what he was learning about the universe with anybody who wanted to listen. He used to say that when you're in love, you want to tell the world, and he was in love with astronomy and space science, and was fortunate to be alive at the dawn of the space age, and to be involved in those early missions. The Mariner mission to Venus and the Pioneer missions to the outer planets and so forth, Viking on Mars. And, he wanted to share that excitement. Initially, he did it by writing through books. And then, by the late 1970s, he'd been a guest on The Tonight Show with Johnny Carson. Those of you who are old enough to remember Johnny Carson, I grew up watching Carl on Johnny Carson, and I read his books as a kid, and that inspired me to be a physics and astronomy major in college, but also to want to write and to communicate. And when he produced the original Cosmos in 1980 with Ann Druyan, his wife, who is the executive producer and writer and director of this new version, of course, with Brandon Braga. The goal was always to make it as visually compelling as the technology available at the time allowed. Astronomy is one of the most visual of sciences, of course. It started with naked eye observations of the night sky, and then was extended by the invention of the telescope. And eventually we learned about the other parts of the electromagnetic spectrum. Herschel, not Herschel, I'm sorry, it was who discovered infrared? The astronomer, it might have been Herschel. He put a thermometer, in the path, and it wasn't Planck, in the path of a prism. It was 200 years and some odd ago, and discovered that the thermometer warmed up even though there was no light on it. And he said, well, there must be some light beyond the red end of the spectrum. So we discovered infrared, and then ultraviolet, and then X-rays and gamma rays, and the microwave and radio wave spectrum, and that extended our senses. But it all began with visualization. And so the visualizations in Cosmos, are really paramount to the kind of storytelling that we do. And one of my roles as a producer on the show, and somebody with a science background, was to make sure that our visualizations done by our amazing special effects team led by Jeff Oken were scientifically accurate to the extent that we could make them so. Some of it is very speculative, obviously, but when we show you a spectrum that and we claim that there is this is the spectrum of an exoplanet atmosphere, and there's methane and oxygen in that spectrum, well, that's a model of what an exoplanet atmosphere would look like in a sufficiently powerful telescope with a sufficiently high resolution spectrograph, right? So, but clearly the idea of making it as beautiful, as visually compelling as possible is part and parcel of how I think you get people excited about the field. And just beyond that, it's the ideas and the stories and the history. I never took a history class in college, which I kind of regret, but working with Ann and the team on this season of Cosmos and the previous season was a great education in history to me, especially the history of science. I learned Maxwell's equations in college without learning a lot about Maxwell or Faraday, and how the one created the foundation for the other, and that was very exciting to me. So I hope that excitement is part of what we're sharing in this show. Not here in the audience tonight, but they are local to LA, some of them, but 15 different, I think, special effects houses from 15 different countries were involved in making this show. It's very much an international collaboration. And, Bouf in France did a lot of the galaxy simulations. When you see the Milky Way, that's this French company that does wonderful, they create point models that, they can use equations from dynamics to model what the Milky Way might look like, and we know something about its structure, so we see it from a distance, and and they can give it a sense of rotation and a liveliness, that makes it very compelling. Lots of other houses all around the country, all around the world, were involved in making these different animations, but the leaders of the teams were here in LA. Both the animation sequences, like with the Lapita people and their Polynesian voyages, and then the digital effects, the cosmic telescope and the Milky Way galaxy, all the exoplanets and so forth. Oh, great. Yeah. Uh-huh. They will tell you everything you want to know. They're more than happy to share what they've done. I don't know. I can. Sure, you can give me my card, and I'll pass your questions along to Jeff. Jeff, maybe he might sometimes speak at places like Santa Monica College. So I'll find out. Sure, absolutely.
So, in relation to the cosmic telescope, so the gravitational lensing, it would allow you to see planets in the past, right?
Yes.
So, how would we know the exact right time to get to a planet when we see it in the past? Because it might look habitable to us now, but by the time we get there, it's not.
Right.
So, how can we predict a planet that doesn't look habitable at the moment, but by the time we get there, it will be?
Well, I think we know enough about the evolution of planets in our solar system, and we've learned enough about exoplanets to have some sense of the timescales involved in the evolution of, for example, planetary atmospheres. So if you're looking at a planet 5,000 light years away, you're seeing it as it was 5,000 years in the past. But it would be really surprising if the atmosphere of that planet changed substantially in just 5,000 years. Now, even our atmosphere, global warming is real and it's a concern, and it will have an impact on the biosphere. But our atmosphere has been largely stable in the most general sense of that term for a couple of billion years, since the great oxygenation event that replaced our more reducing atmosphere with an atmosphere with 20% or so oxygen. That's not going to change in 5,000 years. Other things will. But if you looked at a planet, a billion light years away, if you could see that far, well then, who knows what it's like today, right? Betelgeuse, Betelgeuse has been in the news. Cameron was talking about it. That's 675 light years away or something like that. It could have exploded 500 years ago, and we won't know about it for another 125 or 175 years, right? So stuff like that, yes, the timescale matters, but the atmosphere of a planet like Earth, once it's, become more or less, once it's cooled and everything is settled out, those things change on very long time scales, generally speaking.
Yeah, and for
Betelgeuse.
For Betelgeuse, we know that there's this possibility, so we wouldn't choose a star like that, right?
You're not going to live on Betelgeuse. I'm telling you that right now.
The Industrial Revolution has, been occurring for about 150 years, and carbon dioxide in the atmosphere, parts per million, have gone up by 33% in that time period or something like that. So if we were to continue emitting at that rate for another 4,850 years, I'm less confident that the atmosphere, that there wouldn't be significant changes to the habitability of the planet. Now, hopefully, we're going to figure it out and stop emitting, and but I'm just saying. So you never. I mean, things happen.
That's a valid point. That's absolutely a valid point. I would say that it wouldn't necessarily change the gross composition of the atmosphere in the sense that there would now only be 5% oxygen. It would affect the habitability for people like us if it gets, if a 5 degrees Celsius rise in the global mean temperature of the Earth would be very bad news for our biosphere as it currently exists. wouldn't necessarily render the Earth uninhabitable, but it probably would make it really hard for our civilization to exist, and it would wipe out a lot of species, and it would have God knows what kind of consequences for the oceans, the ocean acidification, and all these other things. But I would say that, yes, a civilization can have a global impact on a planet. I doubt that civilizations are so common that that's the kind of change that's going to happen on any given planet in the habitable zone within a few hundred light years of the Earth.
I guess I will maybe quickly add that we can try and predict naturally how planetary atmospheres evolve, but when it comes to how civilizations affect atmospheres, we have one data point, and so we would kind of be guessing.
Well, no, right, and I'm just extrapolating from that data point.
Yeah.
I'm a little bit circumspect about assuming that something that's 5,000
Yeah.
years away.
So I agree with you that if it is already inhabited,
Industrial revolution and intervening factors.
yeah, and they could have some sort of cataclysmic war that destroys their planet. We don't know.
But I would also ask the question, what are the odds that there is a planet 5,000 light years from the Earth that is 5,000 years behind us technologically, and in 5,000 years will have that level of industrialization and burning of fossil fuels and so forth that would drive them into a climate crisis? I think that part of it is what I would find pretty unlikely. Timing is everything. Exactly.
Yeah, but I bet there's many paths to a climate crisis.
I don't know how many of you have heard of it. There's a book written in the 90s, I believe, called The Millennial Project. The author's name is Savage. I forgot his first name. But it takes you in 8 steps to colonize the galaxy. And it's all science-based. There's no science fiction in it. And it's remarkably, it's still valid today. And it seems like when you look at what Elon Musk and SpaceX is doing, they are stage 1. And you can see what his plan is just to get us to Mars. But if you look at the Millennial Project, and I'm bringing it up to you because it would be a remarkable 8-episode series to take on after Cosmos, because of what he does. But I just wanted to bring it to your attention if you'd heard of it.
Oh yeah, I'm familiar with it. Yeah.
Oh, good. Okay.
It is fascinating, and it's kind of, the Fermi Paradox, right? When the famous Italian-American physicist Enrico Fermi, who created the first controlled nuclear reaction in Chicago in the early 1940s, there was a flurry of UFO reports, and it got him to thinking. And he asked some colleagues at lunch one day, "Where are they? If alien life in the universe is relatively common and technological, wouldn't one imagine that we'd know about it by now, and that they would have been here in an unambiguous way? And given that the universe, they didn't know back then, they could guess 10 to 20 billion years old. A pretty good idea now that it's about 13.8 billion years old. If you extrapolate from what we've done over the last few hundred or couple thousand years, over the next couple of thousand years, it seems pretty likely that, barring disaster, we'll be colonizing this solar system over the next few centuries, and then in the next few millennium starting to move out into the galaxy. And once you start that process, it only takes about 10 million years, give or take, colonize an entire galaxy. 10 million years is a small fraction of the lifetime of the universe. So if intelligent life like us is common and doesn't destroy itself every time, you would expect that they'd be here by now, or we'd know about it in some fashion. And the fact that we don't means it's probably rare. At least that's one way of thinking about it. Yeah. Seth is friends with Elon, actually.
What is the percentage, say, of the same age planets in our Milky Way galaxy with the same level of development that we could possibly communicate now? Or I just want to even know what is the statistics for that?
I don't think anybody has a real answer to that, because we've as Pika said, that we have one data point. There's one civilization that we know about, that we communicate with.
But we do know ages of stars pretty well, and so we can imagine that the planetary systems around those stars are about the same age as the star, give or take. And so when we study planets, we do think about how old they are. We're a little far away from being able to tell if there's life on it, but we certainly take the age of the planets into account, mainly to understand how they form and evolve, but eventually how life evolves on them as well.
Mine's a survey question for the whole panel. We've done Apollo, and then we've varied back and forth between Mars and Lunar. And what's your vote, each in turn? What's your vote for between those two, or a third option? And really quickly, why? Each of you.
Start.
Sure. Well, we have already been to the moon, so I would definitely vote for Mars. Well, in the NASA law, it is like, if you look at the law, it said that we should have go back to the moon by 2020. So it was a plan to go back to the moon. It's just like it got derailed, but it's much easier to go to the moon again than to go to Mars. But I would vote for Mars.
Cameron, do you
I really like the moon. It's as Ilaria said, it's considerably closer, it's considerably easier, and yes, we've been there 6 times. But if you were to land pick 6 random spots on the surface of the Earth and say that you've been there and you've seen all there is to see on the Earth, I mean, it's silly, right? But I realize that this is a significant expenditure for our government, and so you have to pick your projects wisely. But Mars would be amazing. It's just a lot more expenditure and risk.
I would like to go to Mars first, I guess. But, if you'd asked me that question in 1970, I would have said Mars, no question. But 50 years later, and we've not been back even to the moon, I think we got to kind of relearn the lessons of Apollo and the moon landings before we can go to Mars. I would worry a little bit. Although I think you could make the case that doing lunar orbital missions and testing out robotically operated rovers on the surface of the moon from lunar orbit would be a great way to prepare for doing the same thing on Mars. And it's only about a quarter as expensive to send humans to Mars to orbit and operate robots on the surface from orbit where you don't have the time lag than it is to send them there, land them, get them back up, and bring them home. It's the landing from Martian orbit and getting them off the surface that's the most difficult and expensive part of that mission. So maybe you kind of split the difference. And you do orbital missions, you encounter the Mars moons, teleoperate robots on the surface, bring back samples before you send humans down. So that might be an interesting, sort of third choice.
I have a personal interest. I'd be really interested if we can build some telescopes on the moon. So I would like to move to the moon for that regard. Both radio telescopes and optical telescopes, there's really a strong, compelling science to put them on the moon.
Yeah, I kind of like the idea of splitting the difference and sending robots, but sending them further maybe to these icy moons like Europa. As an exoplanet scientist, I think those are the ones that teach us a lot about these other distant worlds.
But yeah, the government has changed its plan many times. I mean, essentially every administration undoes what the previous administration had plans, and so it keeps switching back and forth. But yes, right now the plan under the current administration is to return to the moon in the next 4 years. And a good note, next month they're opening up astronaut applications to potentially have the next class of astronauts who would be manning the Artemis missions, which are the missions that are set to go to the moon in the next, what's that? Womaning. Pardon me. Populating these missions. So yeah, over the course of March, I think the deadline is March 30th, something like that. But yeah, no, it's super exciting. I'm applying. I hope other people are applying. So there was, yes.
Hi, good evening. I have 2 questions for the panel. The first question is, in the presentation there was like a planet that was discovered that there is some life on it that kind of looked like Saturn. Like how would we know if it's inhabitable for humans? And my second question is, if people decide to go into space to colonize, would it be a coalition of all the countries together, or would it be individual countries competing for colonies, like China, Russia, United States, other countries? That's my question for the panel.
I'll try to answer the first part. For us to try to understand if a planet is habitable, the first thing we can do with technology not so distant from now, maybe a couple of decades from now, is to try to take a spectrum of that planet. So we do spectroscopy, and in spectroscopy you can look for molecules. So like we do spectroscopy of things on Earth, you can try to do spectroscopy of other planets. You look for molecules. In particular, you look for signs, things like oxygen, water, carbon dioxide. Then the hard part is, then we have to use physics to understand, is this a signature for life? Is this a signature for a habitable world? Or is this some other sort of abiotic signature? Oxygen, carbon dioxide, water, they can all be produced through abiotic sources, could be produced from like volcanoes, from places that would definitely not be habitable, from planets like Venus also has signatures of these things. So we want to try to rule out as many of those possibilities as possible with our understanding of physics, our imagination, to find the best planets. But at some point, we kind of have to guess from there. If you want to start thinking about further along, maybe somewhere in between the solar gravitational lensing telescope shown in this documentary to somewhere maybe in the next 100 years, what we can do is to try to resolve the surfaces of these planets. So right now we see planets as basically dots in the sky. We have no resolution of their surfaces. But if we were to build much larger telescopes say somewhere between 10 and 100 kilometers in size, we will be able to see at least a couple pixels on the surfaces of these planets. And from there we can start learning about things like, is there land, is there ocean, and things like that. And that it's going to be incremental. It's going to be trying to find the best planets with the current knowledge we have, and then building better technology to narrow that field down more and more and more.
I just want to point out quickly that we mentioned in the episode that planet with the rings that had all of that lovely foliage and so forth, that was terraformed. That was something where we brought life to a barren world that had a potential, for life, because it was in the habitable zone, had liquid water on its surface, maybe like a nitrogen atmosphere. And then we brought Earth life there and figured out a way to make it flourish on that world, which would be the safest way, I think, from a human biology perspective, to colonize another world. If that world already had life on it, I think it'd probably be smart to stay away from it for quite a while until you really understand whether you can coexist with that native life.
And just quickly to answer the second part of your question, right now it is all competitive. It is all the space race. It's nationalistic goals for bringing this country or that country to compete. But we aren't at the stage where we're able to colonize other planets or terraform other planets. We're still trying. I mean, so far we've only been to the moon 6 times with people, and it was all as part of NASA and the United States. But and one might cynically think that the only reason that the U.S. is starting to go back to the moon now is because other nations finally have the technology to be able to go up themselves, and it's driving us in a nationalistic sense, not a scientific sense. So we're going back because now China has said we're going to go to the moon, and other nations have said we're going to go to the moon, and we can't get pushed around. We have to go back. We were the first ones to the moon, and yeah. So one would hope that in the future, when we're able to make more distant voyages and more permanent bases, that we'd cooperate. But one would hope.
Well, But in that sense, like there are already examples of international collaborations. Like most of like the space telescope are not only the U.S. Is always a collaboration between many countries. The International Space Station is a great example of collaboration with many countries. So there's a little bit of both right now, right? The film is a collaboration, exactly.
Way in the back.
Trying to get people who haven't. Yeah, sorry.
So, I thought maybe we could live on Venus's sky, because up there it would be as dense as Earth's atmosphere, and we could use the sun's energy to create a different types of basically floating cities is by using solar technology and using the nitrogen in the atmosphere of Venus to grow crops.
Absolutely. No, there's no question. There is a layer, there is an altitude. If you go to Venus and start going down through those clouds, there is an altitude at which you have a really kind of normal room temperature zone, 65, 70 degrees Fahrenheit, and an atmospheric pressure that's sufficient to allow you to float with some kind of a, like a Zeppelin or a, what do they call the blimps, just like a blimp. And at the very least, we should be sending blimps to the atmosphere of Venus to sample the atmosphere at those levels. There might be bacteria. There might be interesting life forms in the atmosphere. In our atmosphere, there are bacterial life forms floating around, tens of thousands of feet high. There may well be similar kinds of things in the atmosphere of Venus. So no question that you could build, a blimp and, something substantially larger, a floating city that would be, a perfectly good, the upper atmosphere of Venus would be a perfectly good place to build something like that.
Yeah, I think the biggest worries for Venus are the gases in the atmosphere are quite poisonous to humans. So you would need to find ways to bring oxygen and like have a human Earth-like compositions. And how do we sustain that? And then the other thing is that the Venus's atmosphere is very windy. There's strong winds, and how can we engineer a solution that you can, handle that? I think those are big challenges.
Yeah, it's just engineering.
What is beyond space?
Anyone?
Yeah. What's beyond space?
What's beyond space? You want to answer?
Yeah. You're elected.
Okay. Well, that's a very good question. Like, I guess it's mainly like the first question is like, how do you even define space, right? You say what's beyond space, but like, is it infinite? Do you define space as what came out of the Big Bang, or of the entire universe, multiple universes? Like, that's just, we don't know, right? So we know that the universe had a beginning in time, or at least the universe that we know had a beginning in time, but we don't know if it had limits in space, right? So, like, thinking, is there something beyond space would mean that there's a limit, maybe spatial limit to the universe, like, or that we don't know, right? That's a very good question that a lot of people here and a lot of places try to get an answer to, right? And there's many theories, and maybe by exploring the universe that we can see and we can explore, maybe we could get some hints that can help us understanding that question. But I guess the short answer is like we don't know. You want to add something?
That was the hardest question yet.
In this, possible new worlds, the Voyagers brought chickens and pigs and what have you. We're going to have to do that on a much larger scale. So, how do you foresee the Noah's Ark of moving to the next planet, and how do you foresee actually populating that planet? Because there has to be an ecosystem for each of those life forms, to survive in. So, how are we going to get them off this planet? Is it just going to be DNA samples and we'll replicate them on the other side, or is there anything? Maybe it's in later episodes. I don't know, but it's an interesting thing to talk about.
Well, we don't necessarily address those questions in this season of Cosmos. We hinted a few ideas. I mean, in the near term, closed ecological life support systems, cells, has been an active area of research at NASA for many decades, and any future planning for a permanent presence on Mars or even the Moon would probably involve some kind of system of greenhouses, some way of, cultivating plant life that could produce oxygen as well as food, and, drawing water in the case of Mars. We know that there's plenty of frozen water beneath the surface, different locations on the planet. On the Moon, there may be ice in the permanently shadowed craters at the south pole of the Moon, specifically from comet impacts over billions of years. When you have water, and if you can bring seeds and grow plants, and if you have a source of energy, sunshine, obviously solar energy, nuclear power, and there are nuclear power, 50, 100 kilowatt nuclear power sources that are being designed for these kinds of missions, then you've got a foothold. You're still going to have to import stuff, probably for a pretty long time. No one has successfully built a self-sustaining closed ecological life support system. A 3 decades ago, somebody tried to do that near Tucson in this Biosphere 2 project. Didn't work out. It was a noble effort, I think, but really, really hard thing to do. So I'd say that when it comes to the Moon and Mars, it's going to be a slow process, but, like the early colonies, maybe here in the Americas, you're going to have to be resupplied from the homeland for the foreseeable future. But technology is always advancing, and, this idea of terraforming, again, seems like science fiction today, but so did flying to the Moon 100 years ago. So, yeah. No, I would not go without cats, personally. And I would think that, thank you. Yeah, I got the button here. I got a cat in a Star Trek uniform on my lapel here. But yeah, I think that, if you're going to have a large-scale colony, hundreds of thousands of people, probably you're going to have livestock. But of course now we're growing synthetic meat. And maybe that's a more efficient way to provide that, resource on the Moon or Mars than, bringing actual livestock. So, that part of the technology is advancing pretty rapidly, I think, at this point. So it'll be interesting to see 10 or 20 years down the road how they solve some of those problems. Yeah. Yes. I would be hard-pressed to live on anything that I can imagine as a Mars colony or a lunar colony for anything more than a few weeks. It's going to be pretty rough living initially. And a lot of people are, embrace that and welcome it, and God bless them. I hope they do it.
So we don't have gas stations out there in space. Would you feel that there's materials or minerals on the Moon or Mars that could help?
Oh, yeah. In fact, I would say we do have gas stations in space. It's just not that easy to extract what you need. There is water. We don't know how much, but there is certainly water ice, in those polar craters on the Moon, and plenty of it on the surface in the polar caps of Mars and beneath the surface. And when you have water, you have oxygen and hydrogen, which is what fueled the upper stages of the Saturn V rocket that took us to the Moon. And in the atmosphere of Mars, you have methane. And both Elon Musk And Jeff Bezos, who's also building rockets that he hopes someday will take people, to Earth orbit and beyond, they're building engines that will run on methane and oxygen. And it's a relatively simple engineering process to draw methane, or to create methane out of the carbon dioxide in the atmosphere of Mars and the hydrogen in the water ice of Mars. And so most of the proposals for sending humans to the moon are built around the idea that we will actually produce the fuel for the trip home on Mars from the carbon dioxide in the atmosphere and the oxygen in the water ice. Yeah, it's a chemical process. It's been known for 150 years. It's a catalyst involved. I forget exactly how it works. But also a lot of the asteroids. I have a friend of mine, Joel Sercel, who's a plasma physicist. I think he might have gotten his PhD here, actually. He worked at JPL, and he worked on the plasma engine for the Dawn mission that orbited Ceres and then Vesta. And, he has a proposal at NASA to basically bag near-Earth asteroids, things that are maybe 5, 10, 15 feet in diameter, heat them with a laser to boil off the water that's in those rocks. And water is probably the most valuable commodity one could have for exploring the solar system. Because, again, it's fuel. You drink it. You breathe the oxygen. It's like, 80% of what you need to stay alive and to move around out there. So, yeah, those are still being made. The so-called SNAP, I think, space nuclear isotope. I forget what the acronyms stand for anymore. But, yeah, they're plutonium just by virtue of the decay of the plutonium metal generates heat. And then a thermocouple can convert that heat into electricity. Not terribly efficient. There is now a version of that. I don't know if they built prototypes, but they use a Stirling cycle engine to convert the heat into electricity, and it's about 4 times as efficient as the thermocouples. But then there's also just, good old nuclear fission in the form of, uranium, like they do in the nuclear submarines and the nuclear aircraft carriers. And there is a new version of that being developed for space applications by NASA. Whether that will fly any time in the foreseeable future, I don't know.
So just first, I wanted to mention a couple of questions that have been raised. The questions are addressed in a very thoughtful way in a previous Nat Geo series called Mars that had 2 seasons.
I worked on that, actually. I was on the first
was going to
season
ask.
as a writer, yeah.
Yeah, and so I would recommend that to people if they haven't seen it, because it takes a kind of hybrid approach of drama and documentary and tries to approach this in a very realistic fashion, terraforming, growing crops under a dome, living in down in the craters to be protected from radiation and so forth. And I presume that's probably streaming somewhere. The question I have is, so going back to something you talked about earlier about extrapolating humanity's technological advances and that you could get from this to populating the galaxy or colonizing the galaxy in 10 million years. So of all the species I know, human ingenuity is among the best. I mean, cats, then humans, and maybe there are others. But human biology has evolved to survive in the atmosphere and the conditions on Earth. And so I'm wondering whether we really can extrapolate. Obviously, maybe we'll come up with technological solutions, but when we go from the surface of this planet out of our atmosphere, radiation, magnetism, space is mostly empty, but it's very hostile. Yeah. And evolution doesn't necessarily work in a way for it to develop, for us to evolve to live outside of the environment we've evolved to live in on the time scale that would be necessary for us to do that and survive. So I think that may be a limiting factor, and that may be ultimately the reason why, even if there are galaxies or there are civilizations scattered throughout the galaxy and galaxies, that no one's gone anywhere, because that's a big limitation.
Well, the big difference between today and what's occurred here on the Earth over the past 4 billion years, probably, in terms of the evolution of life, is there is now a species on this planet that is capable of directing its own evolution, which is us. And, we know enough about genetics, and we know how to manipulate DNA, even in the germ cells, to be able to change the course of the evolution of the species. I think it's way too soon to try to do something like that, but there are people who are going to. And, my friend Seth Shostak, who is an astronomer and the lead astronomer at the SETI Institute up in Mountain View, searching for extraterrestrial intelligence, Seth is convinced that the first contact we make with extraterrestrial life and extraterrestrial civilizations will be intelligent machines produced by those civilizations. Either the descendants of biological life that created the technology as we are doing today, or some hybrid version of organic and inorganic life. I know there are a lot of people like Ray Kurzweil and others who talk about someday we'll be able to download our consciousness into some kind of advanced computer. I'm personally highly skeptical of that. First of all, we don't understand how consciousness works. It's not just electrical signals, it's biochemical, and there are all sorts of, subtleties and nuances to that we don't understand at all. And I just don't know that how you can claim that it would be possible to do such a thing. You could maybe make a much more robust organic brain and somehow substitute that for your own gray matter and maybe have a longer lifespan and maybe be more resistant to radiation. Maybe there are ways to modify the human body that would accomplish some of that. But personally, I'm skeptical. But who knows what could happen? I mean, look at what we're doing with gene editing, with CRISPR and all these other technologies. It's a brave new world.
Yeah, I'd say that we don't currently understand what are all of the problems, and I think when we understand the problems, we might have ideas for how to solve those problems. So I think it just takes time.
How does a supernova form?
Stellar astrophysics. Yeah, you're a neutron star person.
So, it depends. Like, all stars are born in the same way, right? Like we do, but we all die in different ways, and that the same stars. And but what determines what happens to a star, what's the final stage, it's the mass of the star, how big it is, right? So, for example, the sun is not going to explode in a supernova. Instead, if you remember, it was showing at the end it was becoming this very tiny luminous dot, and that was a white dwarf, right? So the sun is not going to explode. But more massive ones do. And what happens is that, so the difference is that the core of the star, right? So what keeps, so the entire life of a star is this battle between gravity that wants the star, wants to make the star collapse, and some energy that keeps the star up. And that energy comes from the nuclear fusion in the core, right? So there's nuclear reactions in the core that provides the energy for the star to oppose this collapse, right? And as the process goes on, some stars, like the sun, will just stop. So they produce more and more elements, right? Different elements through their lives, and the star will just stop and just become a white dwarf that is this very tiny thing that sustains itself against gravity. But some stars, the core is just too big. It cannot sustain itself against gravity, and so it starts collapsing and collapsing in this catastrophic way. And at a certain point, the core becomes so dense that all the nuclei touch each other and they bounce back. That's when the supernova happens. So you have this huge explosion in which the outer parts of the stars get ejected in this bouncing, right? And what's remain, it can be either a neutron star, which is a very cool star that study, or a black hole. And that also depends on like how much mass you have there. That was a very quick.
This is a question that has been lurking in my mind for a very long time. Okay, Venus is closer to the Earth than all of those other places very far away. Why there isn't enough or more exploration to find out what's down there going through those heavy clouds? I mean, this is closer.
There's a very good reason for that, and it's because Venus has those thick, heavy clouds that the surface of Venus is very hot. It's about 900 degrees Fahrenheit. It's hot enough to melt lead. And the pressure of the atmosphere at the surface of Venus is about 100 times the pressure of the atmosphere of the Earth. There have only been a couple of spacecraft that have landed on the surface of Venus, and they didn't last very long. And one was a Russian spacecraft, and it sent back some pictures, and the camera, had to be inside this specially insulated part of the spacecraft, inside thick metal walls, and they had to have a sapphire crystal window for it to look through, because sapphire was like the only thing that was transparent enough that wouldn't melt in that extreme temperature. So it's just so the surface of Venus is the hottest place in our solar system. It's even hotter than the surface of Mercury, which is like twice as close to the sun. It's what the astronomers called a runaway greenhouse effect. It could be, as we showed at the beginning of this episode, that 4 billion years or so, a few 100 million years after the solar system formed, that Venus had a much more habitable surface, that the atmosphere was relatively thin, and it might have been an ideal place for life to get started. But something happened on Venus. There was volcanic activity, maybe collisions with some other objects, plate tectonics, and it released a lot of carbon dioxide into the atmosphere. And that started this runaway heating effect. It's the atmosphere of Venus is 90-some% carbon dioxide. If we had that same atmosphere here on the Earth, the surface of the Earth would be hundreds of degrees Fahrenheit. That's how good carbon dioxide is at trapping heat. So that's sadly why Venus is inaccessible. People had hoped in the 1950s, when I was a kid, people still thought, well, maybe there's a chance that there's like some steamy jungle world underneath all of those clouds, But then we started shooting radar at Venus, and we sent spacecraft there, and those radar studies showed that the surface had to be really hot to generate the radio waves we were seeing from Venus. And that's sadly, a planet that could have been a great place that just went on a different path. Yes. Yeah, there are a lot of people who are very interested in Venus and want to go back there. And there's a Japanese spacecraft orbiting Venus right now, actually, and doing a lot of studies. You just don't hear about it that much. Yes.
Yeah. But looking at Venus, so I'm getting a hard time because
the evening sky right now.
When you look at Venus through a telescope, particularly when it is as it is now, when it's a gibbous, which is to say larger than a half view, it just doesn't look all that impressive through a telescope. And I've caught a little bit of flack for suggesting that it's not so impressive, but it is very bright. You'll probably see it if you look up in the night sky. Not tonight, but on most nights you'll see it. What looks like an extremely bright star in the western part of the sky just after sunset. And you might think it's an airplane, but it's not moving, but it's extremely bright. It's also known, people refer to it as the evening star, even though it's not a star, or the morning star at other times of its orbit when it appears in the sky. But it's the brightest object besides the sun and the moon in the sky. Yes.
That's right. Yeah.
That's true.
It's too bad it's cloudy. It would have been very pretty to see.
Yeah, it would have been nice.
This is for Arpita and Jason. So back in the olden days, when they were first finding exoplanets, they found them by either small perturbation of the star or dimming of the star as it passed in front. Then a friend of mine, Ben Zuckerman at UCLA, you may know him. He's done this sort of study too. He said that his team was starting to find exoskeletons by directly seeing them, but it wasn't reflective light. It was large Jupiter-sized planets that gave off their own signature of heat, and that's what they were detecting. Can you tell me now, are you actually observing reflected light off of these exoplanets? And if so, what scope are you using?
So the olden days were not that long ago. So I look for exoplanets by looking at the wobble of the star. And we're still... So first of all, it's only about 20 years old, the technology. And we're still pushing on it to be able to measure wobbles that are small enough to find Earth-like planets. So there is a new generation of instruments being built right now that should start to begin to be able to see Earth-like planets around Sun-like stars, the wobble induced by them. And we also do transits, so the dimming of the light is a still new and exciting technique. We are still flying spacecraft to do this and plan to keep doing that in the next few decades. But simultaneously, the most obvious way to look for things in astronomy is to take a picture of it. And so we've been working on trying to image planets directly. And actually, this futuristic technique is what Jason works on.
I'm going to first plug that I'm giving a public talk next month on this. Real images of exoplanets, none of that artist conception stuff. But yeah, so basically we're currently only able to directly take pictures of planets that are self-luminous. These planets have recently formed, so they're only about like 10 to 20 million years old. To give you a sense of how old that is, the dinosaurs went extinct 60 million years ago. So these planets were born after the dinosaurs. So these are really hot planets. They are thousands of degrees. 2,000 degrees Fahrenheit, 1,000 degrees Celsius. Those are the planets we can currently directly image with our current telescopes. These are like 8 to 10 meter telescopes. Keck, all your favorite ones, Keck, Gemini, the very large telescope in Chile, like these are the telescopes. We use the largest telescope in the world to image these. In the future, using either large ground-based telescopes, 30 to 40 meter telescopes, or launching a 5 to 10 meter space telescope, we will be able to image planets in reflected light. So looking for planets like Earth, like Jupiter, that are just reflecting the sunlight from the star. Those are much more challenging. So currently the planets we see are about 1 million times fainter than their star, and they reside. So if you pluck a hair from your head and place it at arm's length and think about the thickness of that hair, the planet resides within the thickness of that hair next to the star. So like this. That's the angular distance between the planet and the star. And right now, these planets are about a million times fainter than the star, the ones we can directly image. The ones we hope to image in the future, in the next few decades, these reflected light planets, say another Earth or another Jupiter, those kind of planets, those are 1 billion or 10 billion times fainter. So 1,000 or 10,000 times more fainter. And you really need bigger telescopes or going into space to make that happen.
Astrophysics is not my field of expertise, so please bear with me. So, from my understanding, it seems to we rely a lot on light as the mode to detect things in outer space. Is there something else, perhaps faster, that can get us to the technology things?
You mean faster than light? Yeah, there's nothing we know of that travels faster than light. There are these sort of hypothetical particles called tachyons, but that's just a sort of a theoretical and not likely to exist sort of idea that people had a few decades ago and played around with. But, the weird thing about if tachyons were real, because of special relativity, they would actually travel backward in time if they were traveling faster than the speed of light. So I'm not sure how useful a tool they would be. Even if we could detect them, great. I mean, I would certainly be happy to look through the eyepiece of a tachyon telescope if such a thing could be made. But yeah, all electromagnetic radiation travels at the speed of light. We look at the universe in these different windows: the X-ray, gamma ray, microwave, infrared, radio waves, and so on, ultraviolet. And they give us different kinds of information about the nature of these objects we're looking at, because the energies involved in making, for example, X-rays and gamma rays so much higher than the energies involved in producing light. Nothing that's warm, no object that's hot makes gamma rays. Gamma rays come from processes typically involving the collisions of atoms and subatomic particles. There's a new window in the universe that just opened thanks to Caltech a few years ago, and Kip Thorne among the people who pioneered it. We can now detect gravitational waves. So when a pair of neutron stars collide, for example, as they did 1.5 billion years ago, they will create ripples in space-time. And we've built instruments now that can detect those ripples. And it requires having a pair of mirrors that are separated by a couple, 3 kilometers, 2 different locations, to sort of make sure that you're not just seeing noise. And a vibration in those mirrors and the path separating, the distance separating them being something like 1/10,000th the diameter of a proton, the nucleus of a hydrogen atom. And we can build detectors that measure such tiny little changes in the curvature of space-time here on the Earth. And that allows us to look at the universe in a new way, opens a new window into understanding processes like the collision of neutron stars or the formation of a black hole. It takes events of that magnitude to create these space-time ripples in a way that we can actually detect them.
So in general, the speed of light is the cosmic speed limit, and I think there's only one thing we observed so far that we might have a theory that might require breaking that cosmic speed limit, and that's inflation. So, if you look at the background radiation of the entire universe, it looks very uniform. And how was it so uniform? So the theory is maybe everything was talking to one another and expanded outwards. But if you looked at how fast space is expanding, it's not expanding fast enough. You need some hyperinflation kind of in the very beginning, but how that happens, we have no idea. I would say at this point, it's a mathematical construct to explain and observable.
Well, kind of.
Well, you still have to bring the entangled particles separating each other.
No, it does not. There is not a signal. That's a really interesting. Well, I would recommend to you a book by Caltech theoretical physicist Sean Carroll, who teaches here and does research here, called Something Deeply Hidden. And Sean's an old friend of mine, and he talks about this, and we talk about it in an episode of Cosmos as well. There is, one of the things that you can say is there were some really elegant experiments that were conceived of by a physicist named John Bell in the 1960s, and then carried out in the 70s and 80s by some other groups, that showed that there can be no local hidden variables. Einstein had this idea. He didn't like the quote-unquote randomness of quantum mechanics. And he said, all right, you can only tell me there's a 50-50 chance that when you send this electron through these magnets, it's going to be spinning either clockwise or counterclockwise. And they said, no, you just don't. It's not even meaningful to ask the question. Until we observe it, it's in a superposition of states. Einstein hated that idea. And he came up with this notion of spooky action at a distance, entanglement. He kind of pioneered that whole notion as a consequence of thinking about this. He said, look, there's got to be something that we just don't know how to see yet, something inherent in that particle. It knows, the electron knows whether it's spinning up or down. Our ignorance is just our ignorance. It's just that. Well, Bell designed this really very extraordinary experiment. It's very hard to explain in a few words, but he showed with using pairs of photons that were created in a, by sending a single photon, like you send a blue photon through a certain kind of crystal, you get 2 red photons, and they will be they are entangled in the sense that if one of them is polarized this way, the other is going to be polarized the other way. It's conservation of angular momentum more than anything else that makes us know that, right? What Bell showed is that you can measure one of those photons. Say you're in LA, you send one photon to Chicago, and you send the other one to Seattle. And if somebody measures that photon in Chicago, he will get a certain measurement of its spin, and the guy in Seattle will automatically know that he's going to get the other measurement even before he makes that measurement. Now, that seems to imply that a signal went faster than the speed of light between the one in Seattle and the one in Chicago. But that's only one way of interpreting that experiment. And what Sean Carroll will tell you is that the other way of interpreting it is that there's a universe where the guy in Chicago measured the spin going this way, and there's another universe where the guy in Chicago measured the spin going the other way. And we just happen to be in one universe or the other. And every time you make such measurements, you're splitting the universe. And that takes away this conundrum of spooky action at a distance, as Einstein called it. And we get into this in a much more eloquent way than what I just laid out to you in one of these episodes of Cosmos this season. So, but the idea that there is a signal that goes from one to the other, that's been ruled out. It could be that space-time has more dimensions than we're aware of. That's another potential solution to that conundrum. Yeah, and that maybe the distance between them is actually, in that particular instance, much less than what we measure in our three-dimensional universe. But it's a really interesting area of physics, for sure.
Unfortunately, it's 9 o'clock, and it's a school night. So, thanks everyone for coming.